The goal of K-means is to find a set of centroids that minimize the within sum of squares. It is intuitive that the more optimally we initialize these centroids, the fewer iterations of K-means are needed for convergence. Also, it will be more likely that we find an optimum solution, that is, the best set of possible clusters. A strategic placement of the initial centroids is therefore of relevance. However, and even though there is a long body of research on clustering algorithms, there is no clear consensus on which initialization algorithm works the best. First of all, it's not clear what best means. It could mean fastest, easiest to implement, best results quickly, best results eventually, and so on. And also, the formal research results have been ambiguous. We do not know for certainty if an algorithm is better in speed or in accuracy, for example, regarding all other algorithms in all possible cases. Since we deal with a problem that is computationally difficult, it is a problem that we call NP-hard, we can only get approximate solutions instead of perfect solutions for any kind of algorithm that we devise for K-means. And this makes it difficult to define the best possible algorithm solution. In this video, we will discuss 4 methods to perform centroid initialization: Forgy placement, random partition, Naïve sharding, and K-means++. Let us see the simplest approach, the randomization of initial centroids from the dataset. This method is also called Forgy Initialization. In this approach, the traditional approach, that is, k random data points are selected from the dataset. These are used as the initial centroids. Obviously, this approach can often result in centroids that are not well positioned throughout the data space, and that can lead to a bad clustering result. But it's still a good and simple approach. Let me give you an example. We have here data in 2 dimensions, dimension 1 and dimension 2, that belong to 5 clusters. The 5 clusters are shown in different shades of blue, pink, and purple. If I select the Forgy initialization, we can get the following initial centroids. And as you can see, the initial centroids represented by the black dots are not representative of the entire space. They are concentrated in the blue clusters at the bottom and in the bottom pink cluster. But what will it happen if I run K-means for 10 iterations based on these initial centroids? Will it converge to the optimal solution, or, in other words, will it find the true clusters? Unfortunately, the clustering algorithm could not distinguish some of the clusters, and it partitioned incorrectly the bottom blue cluster. Even with 100 iterations, the result is still the same. Now, consider that we had selected the centroids in a different manner, as it's shown. If we run the K-means on this set of initial centroids, the result after 100 iterations would be the following. In this case, the groups match the original groupings of the data. This means 2 things. First, that initialization is crucial for K-means, and second, that different initializations can lead to completely different K-means clusters. This is in fact one of the disadvantages of K-means. It is sensitive to the initialization of the centroids. So, if a centroid is initialized to a far-off point, it might just end up with few points associated with it, and at the same time more than one cluster might end up linked with a single centroid. Similarly, more than one centroid might be initialized into the same cluster, resulting in poor clustering. Let us now look into a second method, the random partition method. In the random partition method, we randomly assign each point in the data to a random cluster ID. And then we group the points by their cluster ID and take the average per cluster ID to yield the initial points. The random partition method is known to yield initial points close to the mean of the data. Let us see this in our example. When we run the random partition initialization, we obtain the 5 black dots as centers. Clearly, they are at the center of our data. This will most likely produce bad clustering results. As shown here, we have 2 clusters that were merged, the bottom left ones, and 1 cluster that was incorrectly divided into 2, the top right one. Because of its simplicity and tendency to derive clusters at the center of the data, the random initialization is usually not a recommended option in general. The Sharding centroid initialization algorithm primarily depends on the composite summation value of all the attributes for a particular data point in a dataset. The idea is to calculate the composite value and then use it to sort the instances of the data. Once the data is sorted, it is then divided horizontally into what we call the K-Shards. An overview of naive sharding is as follows. Assume that we place all your data points as rows of a table. Each row is a data point, each column is a dimension. The value of a data point in a given dimension is given in the corresponding cell. For example, data point 1 can have the value 5 at dimension 1 and value 59 in dimension 2. In naive sharding, you go through 5 steps. The first step is to sum the columns for each data point and create a column for this sum in the table. In step 2, you sort the data points, the rows, by the newly created sum column in ascending order. In step 3, you split the table into shards, k equal-sized pieces. In step 4, for each shard, sum the attribute columns, excluding the column created in step 1, compute the mean, and there you have new centroids for that shard, for the different shards. In step 5, you return the set of centroids for use in the K-Means clustering algorithm. Centroid initialization using naive sharding happens in linear time, and the resultant execution time is much better than random centroid initialization. The major advantage of this algorithm is indeed its speed, as it only passes one time for each data point to calculate the sum of its attributes. If we run the naive sharding in our example, we obtain an acceptable set of centroids for our data. When running the K-means, we also reach a good solution. All clusters were correctly identified in general terms. K-means is another popular alternative to the random approach. It was proposed in a 2007 paper, and it works by assigning the first centroid to a randomly selected data point. Then, it chooses the remaining data points, the centroids, based on probabilities that push the new centroid as far from one another as possible. The intuition behind this approach is that spreading out the initial cluster centers is a good thing. The first cluster center is chosen uniformly at random from the data points, after which each subsequent cluster center is chosen from the remaining data points as far from the existing clusters as possible. As shown below, if we run the K-means we obtain cluster centroids that are very close to the true cluster centers. And if we run the K-means on these centroids, we obtain very good clustering results. But let us see the algorithm in detail. We take the data, all the n data points, and we want to choose k cluster centroids from C1 to Ck. We pick the first centroid randomly. For the second centroid, we calculate for each data point the squared Euclidean distance to the nearest centroid. In practice, this is to calculate the sum of squared deviations. After calculating the sum of squared deviations for each point, we pick the point with a high probability according to the factor shown here, where we weight the distance of our point over all the other distances. This is a measure of the relative distance of our point to the centroid. The farther away, the better. And we repeat this procedure until all k clusters are chosen. But wait, you might ask, why do this probabilistically? Why not choose the one with the largest distance immediately? Why pick a random point according to their distance? The answer is due to outliers. There can be outliers in the data which might get chosen over other points. In this way, with probabilities, we try to minimize this possibility. Despite the advantages of K-means++, it has a performance limitation since the K-means++ initialization needs to pass over all the data several times, and it does not scale very well to large datasets. However, this method yields considerable improvement in the final error of K-means. Although the initial selection in the algorithm takes extra time, the K-means part itself converges very quickly after this seeding, and thus, in result, the algorithm actually lowers the computation time. It is good to remember that it does not guarantee optimality. The algorithm can too find a suboptimal solution, it's still an approximation, and also it's more complicated than the original K-means algorithm with Forgy Initialization. But overall, this algorithm is recognized as one of the best approaches to do K-means initialization. With this, we end this lesson. We hope that you have enjoyed the lesson and are curious about the next video. The next topic will cover the general challenges of K-means. Thank you for watching and see you next video.